Hi, I'm Mayur Naik, a professor of computer science in the School of Engineering and Applied Science at the University of Pennsylvania. In this presentation, I will give you an overview of software analysis, an elective course offered as part of the MCIT online program. Let's face it, writing correct software is hard. And in today's world, software errors have an enormous cost. One study from 2016 estimated that software errors cost the United States economy a whopping $1.1 trillion. Some of the notable examples of how software errors cost us include failures of expensive systems such as NASA's Mars Polar Lander, which crash landed on Mars in 1999, and the infamous power grid failure and ensuing blackout of the northeastern United States in 2003. Security vulnerabilities that allow malicious users to steal information from or take control over everything from IoT devices to systems software to web applications, and setbacks to emerging technologies such as autonomous vehicles. Studies have also shown that the sooner a software error is detected and fixed, the lesser the cost. For instance, a bug that is found after software has shipped costs 640 times more than if it were found by the developer while coding. Moreover, the vast majority of bugs, 85% according to this plot, are introduced during coding. These observations have given rise to the prevalent shift left approach in modern software development, which seeks to reduce the cost of software errors by pushing testing earlier into the software development cycle. More generally, modern software development is much more than programming, the vast majority of it devoted to ensuring software quality. For instance, consider Microsoft's software development lifecycle. When a code change is committed via a pull request, denoted by PR, it kicks off a series of processes comprising analytics, code review, issue reporting, continuous integration, testing, all the way to production. And the cycle does not end in production. Most software applications today are continuously monitored, and the data from end users feeds back into the cycle to help improve the next release of the software application. This course is about a body of powerful yet practical techniques and tools to improve software quality and thereby cater to the most pressing need of modern software development. To that end, the course focuses on algorithms that analyze code. We will primarily focus on software quality in terms of correctness, security, and performance, although the methods covered are applicable to other aspects such as code readability, maintainability, and so on. This course will not teach you how to write code, although it will make you a better programmer. You are expected to be fluent in some programming language. I will outline the programming expectations in more detail later in this presentation. This course is also not about how to use prevalent testing frameworks in industry, such as Selenium. While the course will include case studies that discuss such tools, however, the primary focus is on the concepts and algorithms underlying such tools. This will enable you to discern the strengths and limitations of a given tool under a set of real-world constraints, be able to adapt an existing tool to a new language or application, or even develop such a tool entirely by yourself. Let's look at some sample use cases of this course. I will illustrate these use cases by means of Microsoft's software development lifecycle that you saw moments ago. The analytics stage of this cycle involves finding any programming errors introduced by the pull request. You will learn about state-of-the-art methods to systematically find common programming errors, such as buffer overruns, null pointer dereferences, integer overflows, race conditions, etc., by analyzing source code. Moving on to the code review stage, there might be disagreement between the developer and the tester regarding the intended functionality of the program. In this course, we will learn how to specify the intended behavior of each program unit precisely and modularly. We will look at units of code such as loops, functions, and classes. You will also learn how specifications written directly in the form of annotations in the source code can go further than merely improving code understanding. In particular, they can be machine checked by automated tools for finding bugs or even proving their absence. Moving on to the issue reporting stage, one might be confronted with a complex crashing test case that makes it cumbersome to isolate the root cause of a bug. You will learn about techniques and tools for automating the process of minimizing such a test case. You will learn how these methods apply not only to minimizing test cases, but also seemingly unrelated problems, such as automatically identifying the offending code commit in a series of code commits. Next, let's look at the testing stage. You will learn methods to automatically generate tests with high coverage for libraries, protocols, data structures, and multi-threaded programs, and thereby uncover insidious bugs that are otherwise hard to find. As a final example, consider the production stage. Suppose you have deployed a software application and are wondering how to continuously collect feedback from end users and use the feedback to improve the quality of the application. Suppose you have deployed a software application and are wondering how to continuously collect feedback from end users and use the feedback to improve the quality of your application. In this course, you will learn how to crowdsource this important task without affecting end users' privacy or performance. This course is structured into three interrelated parts: lectures, supplemental readings, and programming labs. The lectures cover fundamental concepts and algorithms. These are presented in a language-independent manner using common programming constructs such as loops, functions, and classes. The supplemental readings go deeper into selected topics from the lectures. They typically involve trying out industrial strength tools yourself, but may also occasionally delve deeper into formal or theoretical aspects. The tools in these readings are chosen based on their popularity in industry, and they span a variety of languages such as C, JavaScript, Rust, etc. The programming labs involve implementing lecture concepts in C++ atop the widely used compiler framework LLVM in a Docker container that is provided to you. Here are the different topics that we will cover in the lectures. There are many diverse approaches to software analysis with different strengths and limitations. Together, these topics cover all the dominant approaches, and they will prepare you to determine which approach is best to apply under a given set of real-world constraints. In the rest of this overview, I will elaborate upon the programming labs. The lectures are designed to present high-level techniques, but they elide details necessary to concretely realize them in a working tool for a full-fledged programming language. For instance, the lectures present various algorithms using an idealized programming language or elide corner cases or ignore performance considerations. The programming labs are designed to providing hands-on experience in these aspects and bringing these algorithms to life. To emphasize the spirit underlying the labs, I will use a quote by Richard Feynman, the theoretical physicist who received the Nobel Prize in 1965 for his work developing quantum electrodynamics. Feynman famously said, "What I cannot create, I do not understand." This quote was written on his blackboard at the time of his demise in 1988. In the context of our labs, this quote means that once you have implemented a software analysis technique by yourself, you will understand it thoroughly and be in a better position to apply it or adapt it to different settings and problems. The goal of the programming labs is to solve the same problem using an array of different software analysis methods. The problem we have chosen is that of finding divide by zero errors in C programs. Although it may sound relatively straightforward at first, you will learn in this course that this problem is no easier than, say, finding buffer overruns or race conditions. The methods span all the dominant approaches to software analysis specialized to the problem of checking for divide by zero errors in C programs. Targeting the same problem using different methods will enable you to better compare and contrast these methods. Besides, the methods are relatively straightforward to adapt to problems other than checking for divide by zero errors in languages other than C. There are 11 labs in total, numbered 0 through 10, to be completed in that order throughout the semester. Lab 0 will introduce you to the LLVM compiler infrastructure, atop which you will implement the different software analysis approaches in the remaining 10 labs. These 10 labs are organized into 4 groups: dynamic analysis, static analysis, constraint solving, and debugging. The labs in the dynamic analysis group will result in a prototype whose architecture resembles that of state-of-the-art random testing or fuzzing tools that are widely used in the software industry. We will host a leaderboard competition allowing you to showcase your prototypes and score them based on various metrics on a common set of benchmark C programs, such as the number of bugs discovered, performance, and code coverage achieved. Similarly, the labs in the static analysis group will result in a prototype whose architecture resembles that of modern static analyzers that are widely used in the software industry. We will host a similar leaderboard competition, allowing you to showcase your prototypes and score them based on various methods against a common set of benchmark C programs, such as the number of bugs discovered, the false positive rate, the false negative rate, and running time. LLVM is the most widely adopted compiler infrastructure in the software industry, including companies such as Apple, Facebook, and Google. Like a typical compiler, it consists of a front end and a back end. The front end supports compiling programs in a variety of different programming languages, including the C family, Swift, Rust, Scala, Julia, and many more. The back end similarly supports generating code for a variety of different architectures, including x86, ARM, PowerPC, and many more. LLVM is extensible, and you will be developing each lab by extending LLVM with a so-called LLVM pass, called so because the program being compiled passes through it. A pass in LLVM takes as input the program in an intermediate format, depicted here for an example program that computes the factorial of a number. The pass produces some result, such as whether the input program contains a divide by zero bug or not. Different labs will be implemented as different passes throughout the semester, and some of them will be chained together to produce bigger software analysis artifacts, such as those you will submit to the leaderboard. The course has 3 main prerequisites. First and foremost, you are expected to be fluent in systems programming. The programming labs involve reading and writing code in C++. Therefore, familiarity with C++ would be ideal. On the other extreme, you could pick up the course material even if you are familiar with a higher level language such as Java or Python, but it would entail a steeper learning curve in the beginning. A good middle ground is familiarity with C programming. Most importantly, you should enjoy systems programming and be familiar with using Linux shell commands and virtual machines. You should expect to write around 100 to 300 lines of code each week by navigating the documentation and API of the open source LLVM compiler framework. Second, the lectures presume background and maturity in data structures and algorithms, such as binary search, graph traversal, and big O notation for analyzing the running time of algorithms. Lastly, The lectures presume that you are well versed in the foundations of computer science, such as the basics of sets, proofs, and logic. If this course overview has piqued your interest, I look forward to seeing you in the course. Thank you.